Hello? I don't know if you didn't online. Okay, anyway, so I still need to remind you about the two-page progress. This is a term project proposal, so that if you first is you need to find your student, right, your classmate to form a group, right, and then you can look at what's a typical proposal. I already shared with you about that the previous year's proposal. About the key thing here is you need to do some enough this kind of literature review about specific kind of vibration engineering project, and then what you can do. As I told you, typically for vibration engineering, you may want to think about how to do some kind of simplify the modeling. We talk about 1 degree freedom MCK model, 2 degree freedom, the model, and then how we can analyze specific kind of vibration project, and then try to think about how you can really, if vibration is too big, and then can you think about how to work on vibration engineering to solve the real problem. So this is a typical thing I would like all of you to have some idea about arrangement, right, of this thing. And of course, I have communicate with the Yunzhou Tech, and then so at least they assign one this kind of senior marine engineer, Mr. Dean, to provide this kind of information about this specific vibration engineering project for one unmanned ship, so that at this moment for this particular product, they haven't done very serious this kind of vibration modeling and simulation, right? And because of limit time, sometimes for company, the more important thing is that they have to deliver this kind of product, so that of course I already request this kind of Yunzhou Tech, this kind of engineer to provide critical parameter, right? So for you to think about how to build this kind of a model, right? So that you can try to understand about this kind of two important things, right? First is free vibration analysis. Typically, we mention, typically, if you can just set an MCK model, we can try to look at this kind of natural frequency and vibration mode, right? So this is a typical thing we care. Okay, and then so that and then second thing is force vibration. Once you turn on the engine for this particular Yunzhou Tech, the unmanned ship, there's a diesel engine, right? So that we need to determine this kind of frequency response function, right? And then so that at this moment, I recommend if the student group you want to work on this project, you may consider 3 degree freedom model. I would say it's one of reasonable way to come with this kind of the model for this kind of more thing, because 2 degree freedom, 1 degree freedom may be too simple, right? So that if you try to look at what's the typical structure of this kind of ship, right? So typically, they do have some. If you look at the previous project, then you will notice that. Let me just quickly show you what's the typical structure, right? In here, term project, and then you look at a main ship project. So basically, if you look at the most important key component of this kind of main ship is you have, let me show this kind of, here. So typically for one, we need to consider about the most important component for this kind of whole mechanical system. So that the first is you have engine, right? Engine is one of key vibration source, right? Forcing function. Like for our previous study, we already mentioned, right? So what is it? Basically, you have certain kind of harmonic force, right? Maybe sine omega t, right? So that this will create this kind of vibration, right? And then so that of course engine, and then you have the shaft, transmission shaft, and then maybe additional water jet, and this is most likely this relate to propeller, I would say. Propeller, and then so that at least when we think about the key component or model, I would say this is the first 1, 2, and 3, right? So that this is a thing I think you need to think about how to use the kind of. That's why I propose in the beginning you may want to think about this kind of the minimum degree of freedom. From my point of view, you can think about this. Consider M1, M2, and 3. Right? 3 degree of freedom to capture the dominant vibration of this ship. Of course, if that's necessary, you may consider about additional M4. M4 relate to maybe some critical component in this main ship, which may be optical instrument or some very sensitive equipment for measurement, maybe some LiDAR. LiDAR using laser is sensitive, right? So that from my point of view, I would say 3 degree of freedom will be the first consider 3 DOF degree of freedom model. Will be one of the preliminary way to make assumption and make some simple model. So that once we determine this 3 degree of freedom and CK, then of course the next thing is what we do. M1, M2, M3. And then we should think about how can we determine the K, Y, Kij for this kind of stiffness matrix. And then eventually we determine this M, K, 3 by 3, and here, and then plus additional, you may need to estimate some under damping, right? So this is the way I suggest now to come with some simplified model for this kind of project. I don't know, do you have any question for this thing? Of course, I also try to give you this additional advice from typical product engineering, and then so that what we care is I show you this kind of product, a practical vibration engineering methodology. For example, MADI for product noise and vibration. MADI means M means measurement, and A means analysis, and D means diagnosis, and I improvement, MADI. So that if you try to look at this thing, then this MADI should be linked to our lecture note, right? We have been talking about a series of analysis, right? Chapter 2 to 8 and chapter 12 is FEM modeling, okay? And then we also measurement is related to chapter 10, and then diagnosis. There's one particular section we discussed about how to look at this kind of diagnosis of mechanical system. And then once, of course, there's another thing is MADI plus 3K, right? 3K means that we know what kind of vibration thing we engineering, what kind of thing, and know why we call this kind of vibration problem, and know how can we solve this kind of vibration problem. So this is a typical thing important for this kind of vibration engineering. I don't know if you have any question. for the project? If not, then I think we need to go to the lecture. So we already talked about this kind of a lecture for give you a series of case study about vibration control. So that this give you basically, as it show you that typically we will show you that we have several methods for vibration control: vibration isolation, vibration absorption, and vibration damper, right? So these are, we also show you for different design, we need to think about how we can, for example, to do this kind of analysis, right? So that, I think we described this one before. In general, we will show you there are two kinds of vibration in problem. One is vibration. Vibration relate to mostly harmonic force from engine motor. This is the one thing, right? So that the second kind of vibration engineering problem is shock. For example, you have impulsive loading. For example, for your smartphone, and when you drop on the ground, and you call it a shock. So that and this is a typical thing. Or launch, by launching of this kind of rocket, a space shuttle, and all things. This is a shock isolation, right? So that typically shock require increasing the K stiffness. But on the other hand, we have a vibration control, then if decreasing the stiffness, sometimes it's contradictory to each other. So it's will make difficult to really come with a good vibration control, which can protect against both shock and vibration. Okay, and of course we already talk about this thing. How can we come with two-tick feeder model for vibration absorber? That's something we described. I think we need to skip this. I also mentioned about typical, right? In aerospace engineering, those kind of aircraft engine, so that they do have this kind of vibration absorber. So that the key question is why we need this vibration absorber for the engine? Typical, this kind of aircraft engine require very high reliability. So that if you reliability, that means this engine has to work for many years and without failure. Reliability is critical. If you don't have this kind of vibration control, and then vibration too big, and then definitely you have a harmonic force, and result in this kind of vibration and the kind of stress, right? If you learn about our UG, this kind of sound mechanics of a design of machine element, so we have SN curve. SN curve is related to how we can study cyclic loading or cyclic stress, right? Stress and function of frequency. So this is something correlate, right? SN curve is related to stress strain and function of frequency. N is frequency, omega. So that in this case, with certain kind of harmonic force, because different omega, stress and strain, and function of frequency. Okay, stress and strain, and then so that definitely you will affect reliability of this kind of product or machine. So that's why for all this kind of machine require like long-term reliability, at least 10 years, 20 years, 30 years, so that the vibration analysis and to make sure that it can meet the industrial standard or international standard is required to do. Okay, and we'll show you that this kind of engine has been, right? Pratt & Whitney is one of the top company in the world. Only several companies in the world can make aircraft engine. So that Pratt & Whitney and the Rolls-Royce in UK, and I think only several companies are able to make a very good aircraft engine for real product. Okay, and unfortunately in China we still has the engine for airplanes still not good enough. That's why we still need to import many this kind of engine, aircraft engine for both commercial airline, like in Shanghai, and also the military, this kind of fighter. So this is, I think, one of a big problem. Okay, and last time I was mentioning about design of a vibration absorber. Basically, it's 2D freedom. Okay, use 2D freedom model to consider about this kind of equation of motion, and then in this case, we look at the frequency response function of this kind of system. Basically, original system, we have this kind of M1. Basically, why M1? This is relate to the vibration output for M1, and this is M8, the second M2 absorber mass. And then so that we look at how this kind of vibration amplitude a function of frequency, right? So that in particular, what we care is we want to make sure that once add this kind of additional mass MA, how can we minimize vibration of original mass, right? So that in this case, what we should do is we need to think about how can we reduce vibration amplitude of M1 to be 0. So in this case, we have to choose proper MA, right? Absorber mass and Ka, so that in this case, we can really try to make sure this is close to 0. If this is 0, and then all the vibration will be caused by the vibration of Na, absorber mass. This is one of the key important concept for vibration absorber. And so of course you can see how can we make this 0. Basically is we need to set this particular condition for certain kind of omega driving frequency, and then we need to make sure that KAMA equals this particular frequency, right? So that is the one of a very important way we think about design of this kind of vibration absorber. Remember, we talked about this in the chapter 1. Taipei 101 is the thing, and vibration absorber is also used for engine, right? So that some of the this kind of very important this kind of machine, precision machine, may also need to do this kind of a vibration control. Okay, so that of course in this case we need to understand that the difficulty of this kind of design is clear. We cannot let vibration amplitude of original mass to be 0. So only very small frequency range we have be 0. So that in real thing, that means if you look at the frequency response function, right? And then so in this case, we have a certain kind of this kind of response, and then with certain frequency range. Okay, so this will be delta F or delta omega. This regime is the way we may can let the vibration amplitude become 0. Okay, and then of course the key problem is this is a narrowband single film device, so that in this case it can be only work for certain kind of frequency range. Yeah, of course. In general, we can try to normalize this kind of all the parameter for this vibration absorber design. You define this kind of a mass ratio, frequency ratio, and all things. And then in this case, we can normalize this kind of frequency response function, and then try to come with this kind of analysis. So that this is one important thing we mentioned last time. Of course, in general, right? So that we can solve, because we can solve this kind of frequency, natural frequency from this quadratic equation, and then we can determine out the new natural frequency of this kind of a 2D freedom system, and then this frequency depends on mass ratio mu and frequency ratio beta. So that this is mu and beta here. Okay, beta here. So in general, we can show you that so it depends on the this kind of design. So typically, from there's a rule of thumb. Typically, people, you can, if you have no experience, then you can start this kind of a mu mass ratio to in between 0.05, 0.25. That's a typical way to come with a reasonable design in the beginning. Okay, so that of course different mass ratio, then the result may be leading to different kind of performance. So this is important for all of you to consider about how we can come with a reasonable way for the design of this kind of vibration absorber. So I think I already show you about animation, right? So that typically there's a one, you can look at the online simulator, right? So that try to change. So if we can look at this kind of online simulator, and then you may look at, you can try to have more idea about how this kind of work. Let me show if I can. Of course, we already have all the equation we discussed, right? Because the 2-degree freedom system, and then so that in general, you actually will have an exact solution for this 2-degree freedom system. So this computer doesn't have the Adobe Flash player, so you cannot show this kind of. It's okay, so that at least we have discussed about this kind of vibration absorber design, and then based on using the 2-degree freedom model, we can try to do this kind of design analysis. Okay, and so that if most likely in real mechanical system product, we have some damping. In this case, if we have a damping in the system, not only pure N and K for original method, then we may need to do additional analysis about more realistic case, right? For this case, you see, once you have a damping, and then in this case, you see, we cannot, from this kind of numerator, right? From here we see we cannot let this kind of this one cannot be 0 because this kind of additional term finite this kind of damping coefficient, so that in this case we can never make this, but what we still can reduce the vibration while with this kind of damped absorber design. So this is the frequency response function, normal frequency response function for the damped vibration absorber. You see, with this thing, that is clear. If damping of this system increase, and then absorber may have some trouble. So for the, if the damping is 0.01, you this can see, okay, but and damping, if damping increase 0.1, so that here damping 0.4, you see, if damping is too big, and then so that the vibration, normal vibration amplitude we cannot reduce this kind of vibration. So basically, this is the normalized, right? So that for vibration control, we make sure that this should be in smaller than 1. So this is a quite important thing. And of course, you may want to think about how to look at using this kind of two-tier feeder model to analyze the type 101 case we discussed in the first lecture. Remember when we talk about the type 101, and actually it's one of a classical example, like $1 million project. So that in this case, let me quickly to show about this kind of thing. So in the first lecture, we already show you about type 101 as an example. So that in that example, and then you may want to try to use this kind of two-tier feeder model to see if we can really design the good vibration absorber for type 101. I think this will be a good example and way for you to consider about this kind of practical vibration engineering. As I told you, this is like around $1 million, the project. Let me see. It takes some time to load this the first lecture, but let me. Okay, so we already described about this kind of one example of type 101, so that I do think will be useful for you to think about if you can plug in this M1, original M1, right? Basically, this is M1, and then we have M2. Right, and then try to think about, of course, in this here we didn't show you about what's effective spin constant, so that this may require try to look at some literature and then try to think about how we can come with some basic vibration absorber design for type 101. Again, this project is this kind of engineering project is $4 million. So it is give you some general example how we can try to work on more realistic engineering project. Okay, so that of course once you have a damping in the vibration absorber, this kind of model, and then the analysis can be a little more complicated. So that in general, let me see. You see, this is the normalized this kind of frequency bound function for the M1, the primary mass, and then so that for this case we have a lot more this kind of parameter compared with the original design without damping, and then so that we have a mass ratio, frequency ratio, and normalized damping and G. So in this case, I'll show you that it'll be more complicated to work on this kind of design. But in general, so that we, as I show you here, so that I think if you look at a textbook, like a raw textbook that give you this kind of solution, basically G quadratic equation, so that we can find this kind of optimized design, right, and determine that G basically is a normalized driving frequency, right, and then try to determine, you see, for the port A and B, so that to design this thing, so that we determine the solution. Once determine this kind of thing, and then we can try to find the design of this kind of damp vibration absorber. So that if you want to use this design, basically they already show you, right? So that if you specify in the initial this kind of the mass ratio, so that once you have this kind of assumption about mass ratio, and then we can determine what's optimized this kind of damping ratio, right? And then at the same time we can determine the maximum normalized amplitude of original mass, like type 101. Okay, so this is a way we can show you this kind of way how to do this kind of design. Definitely, see, if we have this kind of type 101 example, you can try to plug in that mass inertia. M1 730 ton, M2 is about this 4.5 tons, so that this can give you an example about how we come with analysis. Okay, so here there's another. Let me show you another topic: rotating machines. So once you have a rotating machine, and then we have additional vibration problem. Let me show here. The whirling. So this is a typical problem for what? Rotating machine. If the speed, rotating speed with some critical condition, and then you will see that the vibration amplitude become much bigger. This is a very simple model in lab model, but at least can show you about this whirling speed, right? When you have a long shaft, and then with this kind of inertia, rotating inertia, then we have this kind of the problem. Okay, so this is very common in real this kind of operation of rotating machinery. I think it really depends on the geometry. If the shaft is soft, more flexible, longer, and then I think that we may need to face this kind of the problem, imbalance, right, for rotating machinery. Yeah. So for this kind of problem, of course, we actually have discussed before, right? So that basically you consider about the inertia, rotating inertia, and then additional this kind of offset of thing, and then in this case, of course, we can also predict what's the critical speed cause a large vibration. Right? If the speed is too big, vibration speed cause a big vibration, it can cause fatigue and damage. Right? So that is quite important, especially for very critical rotating machine like turbine using in the electrical power generation, like used in COP. So once you have a large vibration, you may cause some big trouble, machine failure, and really the company may lose a lot of money. So they do have some recommendation from the industry. For example, NOAA recommend the critical speed should below 150% of design full power. This gives you some basic recommendation. Why? For NOAA means this kind of special organization, Marine and Aviation Operation, NOAA, National Oceanic and Administration in the United States. So this at least can give you some reference, right, for the design. I think this kind of guideline can also be used for this Yunzhou Tech project, right? So that remember we have engine, transmission, the shaft, and then so that if shaft is low enough, then we may have a problem from engine, the shaft, right, to another one. So that in this case, it's important to do some this kind of analysis. Yeah. So typically, so this is also quite important to understand about how can we design the optimized frequency range for rotating machine like an engine or anything, so that if we have under this kind of low frequency range, and most likely it's spring dominant. If you look at this kind of driving frequency omega much larger than this frequency, then it's a mass dominant place, right? So that it can be easily we can easily analyze the kind of system. Okay, so that here this is a general recommendation about how we can try to do control about the natural frequency. As I mentioned, this is a one of way for all the product and R&D engineer to consider, right, control of natural frequency, right? So that in general, in order to minimize the resonance, if a big resonance, you lost displacement, lost strain, and stress, and core failure and crack, right? So that in this case, most likely, typical operation frequency or driving frequency is something we use to drive certain kind of machine. So we cannot change this kind of excitation frequency. On the other hand, we can consider about how to change the mass or stiffness to, in this case, we can minimize this kind of a problem, the resonance problem, right? So that another thing is when we look at M and K, how can we tune this kind of the inertia, the mass may be also difficult. So one of a possible way, most likely, is we change our stiffness in mechanical system. Transit system, maybe the several method we have talked about several times, right? So typically, you may change material, right? For example, if you buy like a 3M viscoelastic material, right? And also number and location of bearing. So this is what we can do, right? To change this kind of stiffness for this kind of a natural frequency. Basically, is what we can change the design is most likely what here. And K can be related to what? Remember, for cantilever beam, we have about 3 EI over L. Why? Why? If you look at the cantilever beam as a spring, so that the L, the length can be affect the spring constant, EI, by the cross-section area. So these are the parameter. Of course, if you can change the material, and then you can change the Young's modulus. So this is a typical way I think we can think about this kind of how can we change this kind of design to minimize this kind of vibration problem. Okay, I think we will want to show you another quite important case study. I will skip this part. And okay, so this is another quite important concept using in vibration engineering. Sometimes we engineer may don't have time look at this kind of complicated design analysis, so that for some, for example, from our textbook, they come with this kind of nomograph. Basically, the design is isolation efficiency equals 1 minus TR, transmission ratio. TR is what we have learned. For example, you have this kind of input frame response function transmission ratio. Okay, so that basically is x, y is related to basically y is excitation frequency n, y, and here this is related to the kind of vibration amplitude, and then it's magnification, and then this is related to how the percentage of the reduction of vibration from 98, 97, 95 to 0. Why? So that of course this is versus relation frequency. So that we need to think about how to come with a visible design. Why? Once you have certain frequency, why? Driving frequency, operation frequency, and then we specify the vibration amplitude, and then the quality of vibration isolator are here, so that you can see this is really depends on this kind of 1, 2, 3 parameter. So that's why if you try to plot this kind of equation in this normal graph, so that so in this case it's easy to work on this kind of vibration design, control design. If you specify the efficiency oscillation, right, and then we can try to, if you know the typical excitation frequency, will determine all these parameters. So this is I think something quite important and useful. Here I show you one additional example about vibration in those machine shop. Drilling machine is one of very common use in our machine shop for mechanical engineering prototyping. So that what's the problem? If a big vibration, what happened to a big vibration? And when we drill a hole, you want to cause some uncertainty of this kind of accuracy of machining. So this it can be a problem for precision engineering. So here I show you about, it turns out in order to do a vibration control for the drilling machine, so that if we have a different kind of a way, the clamping of this kind of this kind of unit, then the result may be different. You see, using some screw and using spring, loaded chuck, and hydraulic chuck. So different kind of clamping. When we do this kind of drilling machine, it will cause some different result. Here I show you about the frequency response function of a different kind of clamping unit, so that you can see. So this kind of thing is not instead of add additional vibration isolator, viscous damper, so that if we change this kind of a different chuck to clamp our workpiece in drilling machine, so that in this case you definitely will change the result. Is a hydraulic chuck. We have this kind of frame response, and then you use some more sophisticated thermal sheet chuck. You see, then the frame response, this kind of bandwidth will be much higher bandwidth. That means we may have a better way to minimize vibration, so that this is show about the importance of this kind of analysis. If you don't do this kind of sophisticated design and analysis, then we don't know this the clamping can really have big impact on this thing. Of course, here I show you about the vibration mode for different this kind of clamping unit. And also, we also need to show you static and dynamic response of this kind of different clamping. So this is something I think is provide you as a better understanding, right? So in terms of mechanical design, first is we try to come with the right mechanical design can perform certain function, but beyond that, functional design is first step. Second one, if we also consider about this kind of vibration, this kind of issue. Okay. Okay, I think we this is another I think normal graph for vibration of solar design. So that again, sometimes basically based on the solution, right? You have two different systems, and actually we can solve the natural frequency as a function of the mu mass ratio I, and then so that this can give you an idea about how we can work on the design in the beginning. Typically, I think it's in this range, so that then we can find that the solution for this kind of our natural frequency of the two different systems for this vibration of solar design. You see, we just show you this kind of thing. So basically, here finally, this animation can give you some rough idea. So when we look at this, it basically is for the middle part, we use classical tune vibration absorber design. So all the vibration will absorbed by this kind of MECH4750. If you have changed that design a little bit, so you can see, then you still have some kind of vibration in original mass. Okay, so this gives you some idea. Okay, so finally here I just show you there's another quite important thing, right? Sometimes we need to consider about human body, whole body vibration for mechanical system design. For example, automotive industry and car. So that we will mention, right? There's a ISO 2631, this kind of standard, right? So that basically they make clear about specify this kind of average observation may have impact on our comfort, right? So the human body, this kind of thing, if less than 0.3 meter per second square, then it's not uncomfortable. But it's bigger than 2 meters square, then extremely uncomfortable. But it's something between here, then it's fairly uncomfortable. So this is a quite important way, right? So that in some product design, we may need to consider about this kind of ISO standard. Yeah. So here this is show you about what's a typical room mean square observation for different vehicle, car, mobile crane, lift truck, tractor, bus, helicopter, and van. So that and mower, lorry. You see different this kind of vehicle, different car, this thing, they do have a different kind of vibration response in terms of room mean square observation. Yeah, of course. Typically, I'll show you. We use this kind of ISO standard for whole body vibration, but sometimes they also use another one, the British standard BS6841, and there are certain design which is similar. Some of design they are very different. Okay, and I think we will show you about this thing why whole body vibration is one of issue. And if you, for example, taxi drive the car all the time, and then if you stay in the car for a long time, it can cause some back pain and blurred vision and insomnia, headache. But even United States, about 8 million people expose this kind of whole body vibration. So that So in this case, how we come with this kind of vibration engineering, make sure that the human body vibration is under certain kind of amplitude, right? Not amplitude, it's a result. Okay, so typically, this is, I think we'll mention this one in chapter 3, so that the human body can be examined as a multiple MCK, mass spring damper system. One of the most sensitive, this kind of part will be abdominal, this kind of thing, 4 to 8 hertz. So that if you have when you are in a car, a big car, and the vibration, the frequency of car close to this kind of 4 to 8 hertz, then you feel very bad, uncomfortable, because that will be, that means cause a lot of this kind of resonant condition. Yeah. Okay, so here there's another quite important direction is shock isolation. As I mentioned, shock is very different compared with the vibration problem, right? Vibration both has a harmonic force and then cause some harmonic amplitude response, right? So shock is in very small period of time, and then you have large, suddenly you have big, this kind of force, impulse force. So basically is that you have certain in short period of time, you have this time and this force, right? So that here can be on the order, I would say 10 microsecond to about millisecond, right? It depends on what kind of a machine. Now we try to examine the kind of shock problem, so that of course in general we study this kind of thing, and then we can try to, if you assume the kind of wanting freedom system, and then we can study the maximum transmitted force during the shock. And here, this is I think one of useful information for all the product engineer, right, to design the real product, so that if you look at high end, this kind of a product or military grade, so this is US DOD, Department of Defense standard for military standard, so that they specify that particular for dignity shock and this kind of how big this kind of shock, and the period, and what's typical waveform. Yeah, here single pass, or you have some kind of sine wave, right? And then specify this kind of the shape, waveform of shape, right? And then try to show this kind of thing. So this is give you I think important reference for you to look at the different standard. So finally here I show you one more. This kind of standard job test is for the electronic industry, like JEDEC. JEDEC is one of important association who provide this kind of vibration standard for most likely for electronic product. So for this one, basically is specify, right, your shop when you do this kind of testing for your product, so that specify hands-on. That means you need to get those some special kind of vibration test machine and program this kind of input half-time, and then this kind of duration is 0.5 second, millisecond, right? And then how big is amplitude? This is 1500 G. So that this is required if you design electronic product for example smartphone or consumer electronic, and then most of this kind of product require you do this kind of JEDEC standard. Okay. And finally, I think we already finished this lecture. I don't know, do you have any question for this particular one? At least I think we have talked about a series of this kind of practical vibration engineering example and give you this kind of the reference, right? I mean, the industrial standard. I don't know, do you have any question? If not, then I need to go to the next chapter. So next chapter is extension. Basically, I show you addition more this kind of case study why some vibration engineering problem. So that here basically is typically why we're facing all kind of machine, different machine. They have here is a table show you what's the typical vibration and what kind of type of vibration. Fan, compressor in the lathe, compressor it may be air conditioning system, engine, hammer, and manufacturing industry. The difference is impact, same wise. So that and then typically here give you what's the typical range of frequency. Why that also quite important. Rubber mat and mount. This is what they use, right? You have some engine, and then some engine you may need to put this with additional rubber mount to minimize this kind of vibration. But typically, rubber or this thing, physical element mostly have nonlinear behavior, nonlinear stiffness. So that, but in general, they have a reasonably good damping performance due to vibration control. And so here, this is also quite useful for a student if you work for building industry, right? For a different building, a different kind of vibration requirement. You see, if for new building, and then it's maybe the maximum velocity, but not vertical velocity is 2 millimeters per second, right? And then and the building on bearing pile, fishing pile is a little bit larger, right? And so for really depends on different type of building, then this kind of requirement will be different. And in your daily life, we will see vibration of different machines, different sources, they're quite different. So traffic car-based induced is 5 to 100 hertz, and acoustic vibration by 20 hertz. Some equipment with the motor is 10 to 500 hertz, and ground a building is much low frequency, it's 5 to 50 hertz. Okay, so this and tall building is much lower, 0.1 to 5 hertz. Okay. So in general, here I show you once a real product from this Vibratech, where you see this kind of hydraulic, this sharp solver. In general, it's a nonlinear, right? The force as function of this kind of velocity. In the beginning, we show viscous damper, most likely is F equals what? CV dot, right? So that this is linear, but in reality, you can see, most likely is in some range, it may be a some kind of linear, but in general, it's non-linear. But of course, we can use, for example, computer or MATLAB can easily describe this kind of nonlinear damping force. That's become not too difficult. And here I show you additional product. For example, this kinetics model, spring isolator, right? So that you see some of this product they specify you in terms of reliability or something. So you see, they specify STMP 117 under the 1,000 hour salt spray, they still can survive. So It's typically for some outdoor this kind of vibration engineering, then the requirement would be much higher because the outdoor you have some rain and other kind of maybe seawater and cause something that cause some corrosion of this kind of vibration isolator. So this can be an important issue for real vibration engineering. And here I show you, there's another kind of product. Torsional vibration damper for the engine. In general, this is also, I think, quite important. Right? As I show you, every engine, car engine, and if you're high speed, then most likely you have this kind of vibration problem. So that then in this case, if you include this kind of torsional vibration damper, then you can really minimize the problem. So inside this kind of damper, there's some viscous oil, like silicon fluid. It's used as good damping material, 45,000 thicker than this kind of motor oil. So this kind of torsional vibration damper most likely can be used in this kind of high-end car, for example, racing car. So that if you can look at the company and then find additional product, right? To see, I think this company, So here, at least you can find, you see, for different company, for different type of car, automotive, this kind of car, you see, they produce this kind of a product for this kind of torsional thing. So this is, I think, quite important for you to consider about this kind of practical vibration engineering. Not only just we saw this kind of MCK, mass spring system, but also how can we really work on the real design and engineering, okay? So here, this is the animation. I think you may want to look carefully. Why? If you have this kind of high speed, this kind of engine, and then under this kind of condition, high speed rotation, and then we must have a most likely a rotating unbalance here. Why? In a big mass, and the other end, we have studied in property chapter 3 and 4, rotating unbalance, and then you cause this kind of vibration problem. And in this case, we may want to add additional torsional vibration damper. So to minimize this kind of stress, when the harmonic force, harmonic stress, you will cause reliability problem, and then this engine may fail rapidly, and then the reliability is a big issue for engine. Of course, we also mentioned that time about those kind of semiconductor industry. For example, Canon stepper, they use for precision photolithography, and then in this case, it requires very, very sophisticated control, right, about vibration in order to make a nano the kind of transistor for the IC chip. Okay, and here I show you one of this kind of specification of this kind of active piezoelectric vibration control system, so that 6 degrees of freedom and bandwidth between 0.3 to 250 hertz. And of course, we also mentioned this TR, transmissibility. Remember, is we look at frequency response function, X over Y. So it's less than, if this is 1 and that's 1.1. So this is something, and then the isolation about 2 hertz is 90%. And one of the critical things is what? The requirement is maximum vibration displacement. It should be very small, 24 micron. Well, remember we use this one to make a nano. transistor for IC fabrication, so that if vibration too big, and then it's very difficult to make a nano this kind of devices on silicon wafer. So here, this is a phase response function from real kind of product. So because this is active vibration control, so that this is a vertical response, horizontal response. Definitely, you can see it's very different from those kind of passive vibration control system MCK. Okay. And of course, now we have the big technology war between US and China, so that this kind of stepper, right, using for example, in semiconductor industry become one of the big kind of a problem, and our central government actually put a lot of money, right, to support this kind of research for this kind of semiconductor. So I believe this kind of thing should be useful for some of our industry, right? If they really want to design our own this kind of stepper for our own semiconductor company, and if you cannot buy those kind of ASML stepper from the Netherlands, and then how can we work on the design and make this kind of stepper? I will say become one of very important thing. Okay, now, and here I show you about the comparison about three types of vibration control system. You have an active electro-pneumatic system, the response, and passive pneumatic system. So that, of course, you can see the vibration amplitude. Passive one is simple design, much cheaper, but it will be vibration amplitude will be much higher. Active electro-pneumatic one is slightly better, and using piezoelectric right, active vibration system, then the amplitude will be much smaller. Remember that time in previous one is about 24 micron, while the amplitude 24 micron. So it's I think it's very important. Right? If your vibration too big, and then how can you make nano transistor? And here it demonstrates about with, you can see, without this kind of active vibration control system for making this kind of nano devices, so that it's clear. Now, if you have no this kind of active vibration system, then you cannot really make this kind of 45 nanometer this kind of microstructure. This shows the importance of this kind of active vibration control system. And of course, there's another branch of vibration control. Here, I show you this kind of the active vibration control has used for legal interferometer. This is one of a very, very like a precise optical instrument. And then so that in United States, and also quite expensive. Actually, you may want to look at what is this thing. Yeah, legal is actually there's a website for this kind of okay, in general, so all the precision machine or optical instrument, while most likely vibration control is critical to see. I also mentioned like another thing is for aerospace engineering. Why now China we have our own international space station now, and then in the space we don't have this kind of air. And then this kind of air damping become close to zero. So that in this case, if have a very large material structure in the space station, and then large means our spring constant we have shown you in the beginning, right? So that if we have a very large space structure, and what happens? You have very large space structure, and then in this case we have our, if it's very big, L and K, if it's spring constant, maybe efficiency of L. So it's the larger and then our K would be much smaller, while we have small K, small spring constant, and become more flexible. So that's why this show you that the importance of this kind of vibration control system for space station. You see, the goal is isolate for this particular RF system, isolate the frequency larger than 0.01 effective in this one. Right, so this is and then you again use this kind of spatial piezoelectric actuator. Yeah. Finally, we also show you another branch application, so that in those kind of CD player, DVD player, or VCT player, so that especially if this kind of used in the car automotive industry, and then vibration can create big trouble. So that the Light On is one of the big company in Taiwan. So basically, they also introduced some special vibration absorber to reduce machine, and so that this is at least one of example vibration control is important for all the airplane, aerospace engineering vehicle, and car vibration, and ship, and not even consumer electronic. All this thing, is important. And typically, we show you how we can come with this kind of thing. Why? In this case, you need to think about how to get those kind of product. Why? For example, this is showing example about this kind of a damper, viscoelastic material polymer, and for example, this company, Polymatech, right? So that they produce a series of this kind of damper for use, especially for this kind of CD, DVD, and then they produce this kind of typical material property like Young's modules and tangent data related to this kind of hysteresis. I think we mentioned this one in chapter 2 and 3. Why? So this related to material damping. Yeah. And of course, with the mention about this kind of vibration isolation efficiency in previous chapter. So typically, now we'll give you what's the typical vibration isolation efficient for different machines, so that this at least this if you for practical engineering sometimes your boss may not give you this kind of a real specification. You may look at this kind of typical industrial standard, right? And then show you, of course, if your air conditioning system and for critical area, and then it's 90% of this kind of isolation frequency, then critical 70%, right? And if using in this kind of steam engine generator and many other things, there are different requirements. Okay, and of course, there's another branch of this kind of vibration is how can we try to have some kind of sensor to sense the vibration of mechanical structure, the building, or some very sensitive equipment, right? So this is showing piezoelectric kind of sensor, which can be used in most likely in very precision, like I will show you here, a piezoelectric vibration control system. And finally, there's another branch is as I show you, like the several in previous chapter, right? vibration engineer usually will use this kind of special kind of polymer like PU, polymer PU4. This is widely used in vibration control and also used for what? Noise control. Because normally, once your vibration is more and smaller, and then the noise generated will be smaller. So this is quite important. But the whole different types of this kind of PU. I think I would mention about that the company right in Germany. That's why they basically will spend $10 billion in Guangdong province build additional manufacturing plant. Most likely will try to make this kind of special polymer for industrial product. So here I show you different kind of material structure in this kind of polymer. Then they will cause have different kind of application. So here you see if you have some kind of special kind of foam with this special structure, you see two-part foam feeder, then can use for engine, right? And open cell foam, this kind of a polymer we're using for air intake and fine grain filter, and can use for the other kind of application. So that for filtration. So here I think this is a quite important, useful information. If you have no experience, at least I provide you this kind of reference. And here they show this another, as I show you like a PU. Why? PU polymer has been widely used in different automotive industry. So that this show you about a wide range of this kind of PU polymer for high density microcellular foam, solid PU, and then they can use for different kind of vibration engineering. In particular, microcellular foam, they can use for car bumper, right? This is vibration control. Okay, so that and this PU foam most likely can be also used for many other components, right, inside the car for vibration control. And here, I think we'll show you these things. Basically, the PU foam is using for car seat, automotive seat, right? And one further here will show you one of this kind of case study. I try to work with UG student for this NAB car. Right? Basically, this is a mobile air platform to measure this kind of air pollution in Hong Kong region. So they have a series of this kind of sensitive equipment. For example, in this car, real-time particle size counter, VOC analyzer, real-time gas analyzer, and things. And these are sensitive to vibration. So that then I let our UG student first to mount those kind of accelerometer and computer that basically is a CVC right the rack to find those kind of sensitive equipment. And then first try to understand the structure of this car. And then we try to think about how they have existing this kind of vibration control with air spring, cold spring, but still it's not enough. So that in this case, this is existing design, but still not enough. 4 cold spring, 2 air spring. And so that we ask our student to mount those accelerometer, commercial accelerometer, right? And then try to do the measurement of the vibration inside car in 3 directions, and then try to go from UST to 70, 70 to 21, and 21 to UST, and then try to measure they can by time response and do the frequency response analysis. And then in this case, we try to, of course, once we measure the frequency response function, and then we can do what? We can try to analyze, right? This thing, and then we identify the natural frequency, right? And then if you know the mass, and then we can use this to simplify the 1D model to estimate equivalent spring constant right? And also determine our critical damping constant. In this case, we consider to add additional viscoelastic damper material, for example, mount A, B, C pneumatic, right? And then show you we can, and then to see how once basically we build a 1 degree freedom model, and if we add different kind of additional viscoelastic mount, right? And then to see if we can have how good is this kind of vibration amplitude on our system, right? To achieve 5 cm vibration amplitude, and then in this case, let's recommend this kind of design A should be used. So this is give you one example how we can show using a simple vibration analysis. We can use 1 degree model and do testing. We can do work on this kind of vibration engineering for this one project I done more than 10 years ago. Okay.